Kia ora Year 11 and 12 and Year 10. You guys are sending in some great requests today. This is one from Connor to do some volumes of solids of revolution problems. And the first one I picked is actually quite a tricky one. So if you're in 13 MCA and resitting AS, I strongly recommend that you watch this question. In fact, if you're in 13 MCA, I'd like you to pause the video now and just work your way right through. And I still think there are probably a few little things that you might want to watch. So just put it on double or triple speed or whatever you need to do. But definitely a really good question, and you can see that it's worth 12 marks. So in this problem, we have to do quite a lot before we get to the volumes of solids stuff. Happily, if you muck up the first 6 marks, you can easily-ish do the second part, right? So in the first part, we have to find the coordinates of 3 points on the graph. And we've got 2 functions. The first is this one, 2y plus x equals 8, which is obviously linear. And the second is a chunk out of a hyperbola. And they intersect at A and B. And so it's pretty obvious that step 1 is going to be to set, well, I hope it's pretty obvious that we have to set these 2 functions equal to each other and solve for x, and then get the y coordinate. For part C, for point C, it lies on the curve, and the tangent to the curve at C is parallel to AB. Okay, so what that means is that we've got the gradient of AB here, and we're going to figure out pretty quickly that that equals -1/2. And what we need to do is to say, well, where on that curve is the gradient -1/2? To do that, we have to differentiate. So I'm going to start with this bit. This first part will probably take, I would have thought, a good 5 or 6 minutes, and then I'm going to go pretty slowly through this next bit, where we have to find the volume generated when the shaded region is rotated through 360 degrees about the x-axis. So this is a tricky, for AS example, of a volume of solid of revolution, because we've got 2 curves here. So we have to think hard about what that volume is going to look like. All right, but let's get on with the first part first. So we've got 2y plus x equals 8. Rewriting that gives me 2y equals -x plus 8. Y is equal to -1/2 x plus 4. That tells me that m is equal to -1/2. So to find point A and point B, well, I can see from point A that the x coordinate is 0, and it's on both the line and the curve. So I can substitute 0 into either one. So to find point A, I used, so we've got y equals 8 over x plus 2. So y here will be equal to 8 over 0 plus 2, which is 4. So A is the point 0, 4. Next, I need to find the intersection of those 2 functions. So what have I got? Well, I've got 8 over x plus 2 is equal to my rewritten function. So is equal to -1/2 x plus 4. Now, lots of ways that you can do this. I did it by getting a fraction for once, actually putting something into a fraction on the side. I have -x plus 8. That gives me 16 is equal to x plus 2 times -x plus 8. I don't like working with this, so I'm going to pull the -1 out the front of this bracket. So it's going to be -1 times x minus 8 times x plus 2. Expanding those brackets gives me this. I get 16 is equal to -x squared minus 6x minus 16. 16 is equal to -x squared plus 6x plus 16. The 16s simplify away, and that gives me 0 is equal to this, or 0 is equal to x squared minus 6x. That's timesing both sides by -1. Factorising that gives me a nice, very easy factorisable quadratic. So x is equal to 0, or x is equal to 6, which makes total sense when you look at the graph. We've already found that this is point A, and so at point B, we've got x is equal to 6, and y we can put into either curve. So y is equal to 8 over 6 plus 2, which is equal to 1. So the coordinates of B will be 6, 1. Right, now the next thing we've got to do is go back and find the trickier point C. We're going to have to differentiate this curve and then set the gradient equal to -1/2. So if I see y equals 8 over x plus 2 and I need to differentiate, I should straight away rewrite it as y equals 8 times x plus 2 to the -1. Differentiating, I get negative 8 times x plus 2 to the power of negative 2. So this is an example of the chain rule where the chain rule doesn't have to do any work because the inside function has a derivative of just 1, right? And I've also had a request for some chain rule practice. I'll be coming back to that in the next couple of days. But for now, this should feel like a reasonably easy derivative to find. So we're setting that gradient equal to this. And that is only going to be true at one place. So let's figure out where it is. Okay, so multiplying everything through, I get first of all, 1/2 is equal to 8 over x plus 2 squared. That gives me x plus 2 squared is equal to 16. Now you could go ahead and expand everything here and then refactorize, or you could just say, well, I'm nearly finished with what looks like completing the square thing. So x plus 2 is equal to plus or minus root 16. X is equal to negative 2 plus or minus 4. So we know that x is going to have to equal... Okay, so we've got those two x values. Sorry for the gap in the video. And we know that we want the one that is greater than 0. So we've got x is equal to 2. And we know that we're at this point here, we're on the curve only. So we're going to put x equals 2 in there. And we're going to get y is equal to 8 over 2 plus 2, which is 8 over 4, which is 2. So point C has the coordinates 2, 2. Okay, so we've done the first part of the question. Okay, so that's the first bit we've done. We've done point A and B, which were from the coordinates we did over here. Right, so there's A, just make it really, really clear to the marker where they are, and here's B. So on to this next bit, which is the part that Connor that you wanted me to do. I'm first going to go over the basics of how we do a volume generated by turning something around an axis when we've just got one curve, right? And that's what we call the disk method. And it's pretty intuitive once you see it. So suppose that I've got a set of axes and I've got this line here. Y is equal to, let's make it go through the origin, y is equal to 1/3 x. If I want to spin that around, I have to turn this stupid function off there. If I want to spin that around the axes, then the way that I'm going to do that is you can imagine that you're going to have a cone that looks like that. Okay, so what we're doing when we're defining this area by integration is we're taking each slice of that cone and we're finding its area and we're adding those areas up to get a volume. So the way that we do that is to think about what's the area of a circle. Area of a circle is pi r squared, and at any point we can think of the radius of these slices as being the height of this curve. So the radius is just going to be y equals blah, blah, blah. The area of the circle will be pi times the radius, which is y, squared. And we're going to add all of those up. So that's how we get a formula for the volume of solid of revolution. So for this example here, what I would do, suppose that I wanted to go out to, I don't know, x equals 9. And you can very easily from this, by the way, find the formula for the volume of a cone. You'll get the integral of pi times 1/3 x squared dx, right? And then we go on and we get pi times, what's that going to be? We've got 1/9, so 1/9 times 1/3 x cubed between 9 and 0, and so on. So that's how we do a simple one. Now this one here is a little bit different because I've got the volume from two different lines. So what we have to think about is suppose that we go from 6 to 0, and first of all, forget about that curve. Just imagine that we're taking this line here, right? So the top line here, and we're making some kind of vase by rotating it around like that. Then instead of just that being the final answer, what we're doing is we're going to hollow out the volume made by rotating the curve. So now what we're thinking about is taking away a second volume. And if you think about it like that when you're in the exam, you're not going to make by far the most common mistake with these problems. So the volume, we're going to have the volume here, the volume of the whole thing is going to be equal to V1 minus V2. And V1 is what we get from the line. So it's going to be this, it'll be pi times, what was my function? So negative 1/2 x plus 4 squared, right? So that's my radius here, at every tiny little slice, and then I'm integrating with respect to x. So that's v1, and now I'm going to hollow out v2. So it's the integral between 6 and 0, and it will be pi times, what was it, 8 over x plus 2 squared dx. And we work both of those out separately, and then we take one away from the other. So I'm going to do that correctly, hopefully very quickly, and then I'm going to show you the biggest mistake that people make with these. And I'm just going to tell you not to do it, and I'm not going to have time to explain why it's wrong, because I need to do some GeoGebra to do that. Okay, so I'm going to save that for another video. But in this case, we're actually just about there by setting up these integrals already. So this first one, it's worth taking a little bit of time to expand this slowly. So when I expand this quadratic, I'm going to get positive 1/4 x squared minus 4x plus 16 dx. I'm going to finish this one off here before I do v2. That gives me pi times, it'll be 1/12 x cubed minus 4 over 2 x squared, which is just 2x squared plus 16x integrated at the limits of 6 and 0. So if I go ahead and do this one now, what do I get? Well, I get 6 cubed, which is 216 divided by 12 minus 2 times 36, 72, plus 16 sixes gives me 96, and I've got 0, 0, 0 for my bottom limits. So when I whoosh all that through, this is 18, and this is 96, so it's 114, take away 72, so this gives me 42 pi for that one. If I now turn to this one, now this looks bad, but it's actually not bad. This is the integral of not 8, but 8 squared, so 64 x plus 2 to the negative 2 dx. So that's equal to 64 divided by pi times the integral so we're going to raise the power by 1, x plus 2 to the negative 1, and then we times by negative 1, because when I differentiate that, I get a negative and I don't want it. If you're watching this, hopefully by now, that last thing I said makes lots of sense. So we get 64 over pi divided by negative 1 over 6 plus 2 minus negative 1 over 0 plus 2. That gives me 64 over pi times negative 1/8 plus 1/2, which is, something's going weird. Let's see, 1/2 minus 1/8. So 64 over pi times 3/8. Yep, that's right. Okay, so that gives me 24 pi. So V1 minus V2 is my total volume. Okay, don't go away. I'm going to tell you what the big mistake is that people make. So it's that minus that, which gives us 18 pi, which is a lovely exact value, and it's units cubed. Right, so the thing that people do wrong here, and it's really easy to do it wrong here, is that hopefully by this point in the course, you've got really good at finding the area between two curves. And when we do that, we just go f of x minus g of x dx. So the trap that people fall into is that they think that they can find the volume. I'm just going to put a big no before someone copies it down by doing this. Find the difference between the two functions and square it, right? But that gives us a completely different shape. So this does not work. So don't do that. Think about it as the big shape minus the hollowed out shape that we're going to take away. Right, so kind of hopefully that helps a wee bit. It probably goes quite a bit further than what you wanted in one video, because this is one of the harder examples that I've found in the AS papers. So guys, if you're following this and that all made sense and you can do that question confidently, you're starting to get into good shape on these sorts of problems. The only other kind of problem you're going to get with these is when we're integrating around the y-axis, and the only thing that changes there will be that my limits will be, there'll be y limits, and I'm going to have f of y here. So I'm going to have pi times f of y squared dy. I'll do one of those another day.